Hello, welcome to our introduction to the ESTeam RF design program. This is basically just a brief tutorial on what the program is and how to do it, and then we're going to actually walk through some examples of it to kind of give you some guidance that you can use, as you use this tool. Now, when we look at the successful wireless solutions and how to deploy those, it's really a three-step process. We have the RF network design. You basically have the radio site survey, and then the actual installation and commissioning. Okay, today what we're concentrating on is simply the RF network design. And really what this is, it's a software feasibility study. It's really a math model. And what we're looking for is the anticipated signal levels. We're looking at achievable data rates. We're looking at any sort of warnings that would pop up that would cause us to have to make some changes to this network design. And really what we're looking at is this particular network feasible. And so what we've done is we've created the RF design program. Okay. And what we designed this for, or what we produced this for, is to really kind of take the marketing fluff out of a very mathematical world. And what we're looking for is expected RF system results. This is things like the received signal strength. It's the fade margin. What kind of an RF data rate can you expect? We're also looking at what kind of a path loss calculation do we have in this so that we can determine whether this is going to work. Now, we wanted to create a very simple tool. So really what this is, and it is available for download from our website in the Resource Center, is it's just a very simple Microsoft Excel template. A couple points here regarding that, if you're going to download this and use, is that in order for everything to function correctly, is the macros need to be enabled. And so this might require you to make some adjustments to your security settings, depending upon how you have that set up. So what this actual tool does is that we have multiple different RF design tools within different tabs. And really the RF path calculation tools is divided into two different sections. We've got one tab that addresses our Horizon series, in which there are multiple data rates that are achievable based upon how much signal. It also incorporates the multiple power levels that go into that, and what they refer to as an average power with the OFDM modulation. In another tab, you'll see that we have used for calculating the Edge 900 as well as the Model 195 narrowband series. Now, these are single data rate devices and single output power. So really the big thing what we're looking for is signal strength as well as that fade margin. Now, beyond just those RF path calculation tools, we've also included some other useful tools to use within your RF network design. We've got an antenna beam width calculator. We have, for the Horizon series, a throughput effective data rates. And really what that's looking at is as we expand that network and we have repeaters or a mesh network, is what impact does that have on the total effective data rate? Then we have a Fresnel zone calculator. We have single calculations within this, such as power conversions, i.e. doing dBm to watts. Then we also have a distance calculations in there where we can measure the distance between two latitude and longitude locations. Now, all these tools are basically in there, and the whole purpose of this video is to actually show you how to use that. So what we're going to do is we're going to kind of go through an example of this, and what we've chosen to do is just a very simple 900 megahertz application. It's a 4-mile link. We've got line of sight between those antennas, and we have a structure, or at least we're anticipating a structure, of 35 feet on each end for our antenna mounting. What we're looking for is just the results that can be expected. Now, at 900 megahertz, ESTeem offers two different products. We have the Horizon 900 and we have the Edge 900. And what we're going to do is we're actually going to look at both of those different radios and what kind of a results would we actually get. And so what I'm going to do now is I'm actually going to turn this over to Eric, and he's going to walk you through using this tool and applying the information into that calculator so that we can get a good idea of feasibility. So Eric, I'm going to go ahead and turn it over to you.
I appreciate that, Dan. Thank you. As you can see here on my screen, this is actually the tool that Dan was talking about. This is the RF design. This is in Microsoft Excel, and it can be a little intimidating when you're first looking at it. But we're going to go through each one of these sections, and you'll see that most of this information is actually the display portion of how the actual calculation is. The different tools that Dan was mentioning are actually just different tabs here across the bottom. So you've got the horizon path analysis, the 195 narrowband and edge, Fresnel zone, beamwidth calculator, horizon throughput, and we'll quickly go through each one of those to see what the benefits are. But really the way this works is that what we see here, everything in this white section up here, is actually the results. This is actually what when you do a printout or you save this as a PDF, this is actually what's going to be shown within that to give you the results of what we calculate. Everything that we enter in here is actually put into this yellow section, which is this data entry keyboard. And it's actually quite simple. It's actually laid out those items that are common between both sites go in the middle, and then we get the specifics for sites A and site B. So let's go ahead and run down this. It's easiest to start down the center. The date is automatically going to be entered in. You then start with the frequency. As if you hit the little drop down, these are all the different frequencies we have available in the Horizon series radios. As Dan mentioned, we're going to look at our first one in the 900 megahertz band. The distance between the two is, of course, going to be common, so we put that at 4 miles. You can put any project name you want in here. That's actually what's going to print on that PDF that you create. And ultimately, then we just select which radio we want to use. Well, the Horizon 900 can actually be run at 3 different beam widths, bandwidths. And depending upon those will affect the power, how much signal strength is required. So what we'll do is we're going to look at it's shipped with a 10 megahertz wide bandwidth. So we'll go ahead and start with that and adjust from there if necessary. We also know that each one of those sides, side A, side B, we now need to select which type of hardware we want to use. Well, we actually have 2 different ways that we can mount the radios. The first one is we can actually mount the radio in what we call a pole mount configuration. It's a very simple, very clean and compact way of mounting the radio. We have an antenna either directly mounted to the radio itself or with a small piece of coax cable. We also can do within that Horizon 900 what we call more of a classic, what everybody understands about it is also the enclosure mount, where the radio gets mounted in an enclosure, either to a sidewall, into a DIN rail mount, and then we run a coax cable up to an antenna. The Horizon 900 can do either one, and what we're going to do is we're going to take a look at the effect of having each one of those and to get the results we want. What this tool is doing is this allows us to make modifications to this wireless network from a math modeled side to where we don't have to install it and raise towers and change locations. This gives us a point of starting the network without and doing the math model analysis side so we don't have to make these changes in the field. So what we can do is let's see actually what this looks like. If we go in and say, well, we want to do this point-to-point connection. So we're going to use a directional antenna at both sides with a pole mount. So we go down our list here of these are all the antennas available for the Horizon 900. The first directional antenna we see here for antenna and pole mounting has a 6 dB of gain. Well, we'll put one of those at each side. So we'll put our gain in here at 6 dB on one side, 6 dB at the opposite side. We also need to calculate in the loss in that cable. Even if it's a small piece of cable, there's going to be a certain amount of loss to it. So then we need to change this so it's a 3-foot piece of LMR 195. So we put in 3 feet, we hit the antenna type, hit the little drop down. You can see that there are many different types of coax cables listed here, and we want to put in LMR 195. So we put the same thing at the opposite, 3 foot, LMR 195. Now what we can see here on our results page is we actually have data rates up to 28.9 megabits per second into the green. In other words, we're going to be able to make this link at 4 miles with the equipment that we've selected. We're able to get a very high data rate. But the first thing that we notice here is that we've got 2 red warning boxes. And this is actually coming from what's called the Fresnel zone. These higher frequencies, as they radiate out, of course, they don't radiate out in a perfectly straight line. They actually create kind of a wide pattern. Well, if you look at the effect of this wide pattern on two antennas, it creates kind of this football shape, this ellipsoid. Well, what happens is that if anything is within that ellipsoid, we have the potential to cause what's called a destructive reflection. It reflects off of it and arrives at the antenna, could potentially be out of phase. So what we want to do is we want to eliminate any of these potential problems we run into in the Fresnel zone. So what does this actually mean? Well, our antennas here are at 35 feet apiece. The Fresnel zone, the height of that, and we're only worried about the first 60%, that's why we even put that on there, is at 45.2 feet. Well, what that's saying is that in the center, in other words, that the longest, at the highest point of that Fresnel zone, we have the potential to run into, in this particular case, if both of them are the same height, it could actually be the ground is actually at 42 feet or 45 feet. Now, the whole point of this is that this Fresnel zone calculator will allow us to make or see the effect of what this is. So let's roll over to this. As I mentioned to you before, it's at 900 megahertz, and of course you can look at it at any given frequency. This is assuming of that 4-mile length that we have 2 miles on one side and 2 miles on the opposite for 45 feet. Well, the problem, or what may be the obstruction between the two, may not actually be at the center. What may we be concerned with may be very close to it. And so as you see here, it runs under the curve. So let me show you the effect. Let's say if our obstruction is only 0.25 miles from one side, that makes the opposite side 3.75 miles. So the length of that is only 22 feet. Well, in our particular case, at 35 feet at both sides, that's not going to be a problem. But we also really don't know what the effect is going to be. So the easiest way to clear this is make sure that we have heights at both sides that will clear this Fresnel zone, at least as far as the design side. This again, of course, is just a warning. As Dan mentioned to you, this is the first phase in designing this RF design. If you go out and take the measurements on it, this may not necessarily be an issue, but we know it can potentially be a problem. It's something we need to be aware of. So when we're in the design side, we can actually just essentially eliminate this as a potential problem. We can do that by simply raising the antenna height at both sides above that Fresnel zone. So if I take the height over here to 46 feet at one side, and 46 feet at the opposite side, you see here now that the Fresnel zone warnings are gone. Now, what does this actually telling us? Well, this radio, what it's going to do is it's going to go as fast as it possibly can based upon the signal strength it's receiving. Well, at the highest data rates, and that's one of the reasons that Dan mentioned it, is the OFDM modulation changes the average power level based upon how high of data rate it goes. So that's already calculated within the tool. So it's not something that you have to calculate outside. That's why it actually then changes based upon the amount of throughput we have. If we look at this and keep the type of hardware that we have selected, we can expect a 28.9 megabit per second link, which ultimately is going to equate to about 14.5 if you're running it through a copper cable. The 28.9 accumulates everything from turn on time, stopping time, encryption, everything that as far as the overhead goes. Okay. Now, if that is going to be sufficient as far as a throughput on the link, that's great. Maybe you're only running a single camera or multiple cameras out there, and 14.5 megabits is plenty enough. Great, we're actually done. But let's say, what is the effect of this if we make some changes to it? Well, let's first take a look at what would this look like with our other 900 megahertz radio? Well, their other 900 megahertz radio is the Edge 900, and it only runs at one particular data rate. So we'll actually use this second tab over here. We then go through the same thing. We've got the date, we've got the frequency, we put in the distance between the two, and we select the radio. Now, the only difference here is that we only have one data rate, receive signal strength, and power level. So you can enter those values in here. The change is that we know that we're going to need a much greater height because we still have our Fresnel zone warning here at 35 feet. So we need to actually raise that height. Let's just go ahead and make it 50 feet at both sides, just to cover that. Well, to do that, we also know that we need going to have a higher or a longer piece of coax cable between the two, because every piece of coax is going to add a certain amount of loss to it. So if we look down here, the antennas that are available to us, well, this one here, we've actually got an 11 dB gain antenna, which we can enter in at both sides of the equation, put in the coax cable, 50 feet of, say, an RG8, 50 feet of an RG8 at both sides. This then gives us a result up here at the top of a fade margin of 30.2. Ideally, what we're looking for in these spread spectrum radios is anything above a 3 dB fade margin will give us a good long-term operation. For reliability, we like to see about a 10 or more dB of fade margin for a long-term operation. So what does this look like if we actually go back and change some parameter in the horizon? Well, you can see it's very dynamic. Everything that we put in here, made a change to, changes the individual fade margin. Well, for this particular example, let's say we're actually going to be running this in a cabinet mount. Well, in a cabinet mount, what we can do is we can actually change to a different antenna type. Let's say we wanted to get the maximum throughput we can possibly do. Let's change this antenna type to 11 dB at both sides. But we also then need to increase the cable length. So let's go to a 50-foot piece of RG8. Okay, as you see, these numbers jump every time I make a change to it. 50-foot piece of RG8 cable at this side too. We can see here that what we did by changing the gain at both sides, even though we're in a cabinet mount configuration, we actually were able to increase the actual throughput of the radio from 28.9 to 36.1 megabits per second. So as you can see, this is a very dynamic chart, but this gives us the ability to determine exactly what we expect to see when we put in the radio with a particular type of hardware. The last thing I want to do is go over quickly some of the other tools that are available to it outside of the two RF path calculators and the Fresnel zone calculator, which we already used. The beam width calculator allows us to determine if we've got a very high antenna at one side. What happens is in a higher gain antenna, you get what you call a vertical beam width. So we need to know, based upon the height of the antenna, how far away from that antenna do we need to be before we actually hit that beam. Well, what this tells us then, if we put in a 900 megahertz frequency band, we select an antenna that we have at 900, an omnidirectional pole mount, say at 22 degrees, but our antenna's at, say, 200 foot in the air, that means we need to be at least 1,024 feet away from it to hit the ground level. All right? So these are very, very powerful tools if that's the potential you're running into. The next thing we need to look at is throughput. Well, what happens is that if you've only got a single calculation, it's pretty simple. So we calculated out that we're going to be 36.1 megabits per second between radio 1 and radio 2. Very easy. But you get into a larger mesh systems, you may be going through 2 or 3 different radios. So let's say on a secondary link, we have 21.65, and on a third radio, we've got 10.85. Well, the effective data rate from radio 1 to radio 4 is a lot more difficult to calculate. So what we did is we actually put this into a chart that says, if I'm going to go through these two repeaters at this given data rates, my end-to-end data rate is actually going to be 6 megabits per second. So it's just a very quick way of seeing what you can expect as far as the throughput. The last one is actually very simple calculations, where it allows you to put in different values in dBm, give it to you in microvolts, watts. These are just different units of measure, everything from feet to meters. The last piece that we wanted to put here is that the horizon, everything that we did here was in the imperial units. You can actually do all the calculation in metric units also. So everything will be in kilometers, meters, and et cetera. So as you can see here, this is a very, very powerful tool. It allows you to make a lot of modifications to a system without having to do the installation. And it is always the first step in designing a very reliable wireless system. So if anybody has any questions, we'll be more than happy to help you go through these, look at your analysis. But again, keep in mind this tool we do keep available and provide to you for free from our website. So if you have any questions, please let us know. But overall, thank you very much.